Welcome to this explainer on the address type and common operations, produced by Forge College. If you're following along in our track, Solidity from Zero, you know we're right in the middle of the Data Types, Structs, and Mappings module, specifically our Introduction to Solidity data types. Well, today, we're rolling out the blueprints for one of the absolute most critical foundational components in all of Web3, the Solidity address type. You know, if you're going to build secure, robust smart contracts from scratch, you've really got to master this one. So let's boot up the systems and dive right in. So let's start with a massive question. How does a smart contract actually know who you are? Just imagine it. You've written this brilliant automated piece of code and it's just sitting out there on the blockchain. When a transaction comes knocking at its door, asking to, say, withdraw funds or change a critical setting, how does the contract securely identify whether the caller is the rightful owner, just some random user, or maybe even a malicious bot? Well, that exact problem, that's what the address type solves. Okay, here is the quick blueprint for today's explainer. We've got 6 core components. Number 1, the blueprint of identity. 2, regular versus payable. 3, the zero address ghost. 4, the bouncer, msg.sender. 5, humans versus contracts. And finally, number 6, building the ownership pattern. Section 1, the blueprint of identity. What is an address? Think of the address as the foundational ID badge of the Ethereum virtual machine. So what is it technically? Well, an address in Solidity is a 20-byte or 160-bit value. It's the absolute unique identifier for either an externally owned account, like the wallet app on your phone, or a smart contract account that's sitting on the network. When you see it in your code, it usually shows up as a hexadecimal literal starting with 0x, followed by a long string of characters. And that string, that's your digital fingerprint. Now, what's really interesting here and absolutely crucial to remember is that number, 20 bytes. You've got to remember that exact size. If you recall our previous lesson on Booleans and logical operations, you'll remember just how incredibly strict the EVM is about exact value matching, right? Well, addresses rely on that exact same strict logic. You are comparing 20 specific bytes of data against another 20 bytes. There is literally no close enough in smart contract engineering. Which brings us to a real golden rule of Web3 engineering. Treat addresses as identities, not numbers. I mean, even though an address is technically a 160-bit hex value, you should never ever try to perform math or arithmetic on it. You don't add, subtract, or multiply addresses. You just compare them using those strict Boolean equality operators we wired up in the last lesson. Section 2. Regular versus payable addresses, 2 types of badges. Okay, so now that we know what an address is, you need to know that in Solidity, they actually come in 2 totally distinct flavors. We've got the plain address and the address payable. A plain address simply identifies an account. But here's the catch, it cannot directly receive Ether. It's perfectly safe, sure, but it's financially inert. On the flip side, an address payable explicitly exposes the transfer and send methods, meaning it actually has the clearance to receive funds. By keeping these completely separate, Solidity forces you to explicitly cast a plain address using the payable function if you want it to handle money. And honestly, this is a brilliant design choice, because it prevents you from accidentally blasting Ether to an address that was never meant to hold it in the first place. Section 3. The zero address ghost, the void. Let's transition to a slightly spookier concept here, uninitialized state. I want you to meet address 0, often written as address, parentheses, 0, parentheses. This is the canonical null address. It's essentially the ghost in the machine. You see, when you declare an address variable in storage, but you haven't actually assigned a value to it yet, the EVM just defaults it to address 0. It represents a missing participant, or just a completely uninitialized state. So how do we actually handle that ghost in our engineering? Well, because address 0 is a perfectly valid 20-byte string of zeros, you must constantly check for it. Using the Boolean equality operator we learned previously, we can write a simple if statement. If some address equals address 0. And that little guardrail right there, it ensures we don't accidentally assign ownership to the void, or, try to interact with a participant that simply doesn't exist. Section 4. The bouncer. msg.sender contextual addresses. All right, it's time to introduce the most important contextual variable in all of Solidity. Seriously, think of this variable as a heavy-duty bouncer, just checking IDs at the front door of your smart contract. That bouncer is msg.sender, It's a globally available variable that always resolves to the immediate caller of the current function. It dynamically tells your contract exactly whose ID badge just initiated the transaction. So if you want to know who is turning the gears of your code at this exact millisecond, msg.sender is your answer. But, context is literally everything. msg.sender actually changes its identity based on how the function is called. If a human user with a wallet calls your contract, msg.sender is that user's externally owned account. But if another smart contract calls your function, msg.sender becomes that other contract's address. And importantly, during the one-time deployment of your contract, msg.sender is the address of the person deploying it. Oh, and as a quick aside, always use msg.sender for access control rather than another variable called tx.origin. tx.origin can easily be spoofed by malicious middleman contracts, so just stick to the bouncer. Section 5. Humans versus smart contracts. Knowing who is at the door. So our bouncer knows the address of who is at the door, but sometimes we need to know the true nature of the caller, like are they human or a machine? Consider this fundamental difference. An externally owned account, or EOA, is operated by a human holding a private cryptographic key. They can independently sign transactions. A contract account, however, has absolutely no private key. It's entirely controlled by its compiled bytecode, and it cannot spontaneously produce signatures. It only reacts when poked. And depending on the architecture of your dApp, you might need to treat these two entities very, very differently. The crucial point here is, how do we actually tell them apart in code? Well, we can inspect the size of the code living at the address using address.code.length is greater than 0. If it has code, boom, it's a contract. But as your chief engineer today, I've got to warn you about a notorious false negative loophole here. When a smart contract is in the middle of being deployed, like during its constructor phase, its code length is technically 0. So a sneaky contract could actually bypass this check if it calls your function while it's still under construction. Always engineer with that edge case in mind. Section 6. Building the ownership pattern. Putting it into practice. All right, let's head to the assembly line and put everything we've learned today into practice. Here is a classic ownership pattern snippet you are going to see absolutely everywhere. First, we declare a state variable, address, public owner. Next, inside the constructor, which, remember, only runs once upon deployment, we assign owner equals msg.sender. Boom, the deployer is now the boss. Then, for any sensitive functions, we set up an access guard. Require msg.sender equals owner. If anyone else tries to call it, the transaction reverts. No way in. Finally, if the owner wants to transfer power, we use an init guard. Require new owner is not equal to address 0. And this ensures the boss doesn't accidentally hand the keys to the entire operation over to the void. I highly recommend you take a snippet like this and test the blueprint locally. Boot up an environment like Remix, compile it to version 0.8.0, and deploy it. Call a helper function to see if address 0 triggers a true Boolean. Then check the contract's own address to see if your code length check returns true. Let me tell you, it is incredibly satisfying to see these abstract identity gears locking perfectly into place and spitting out the exact Booleans we engineered. Okay, let's recap the core schematics of today's explainer. Addresses are 20-byte identities, and absolutely no math is allowed. You must use address payable if you intend to push Ether around. Your absolute best friend for access control is msg.sender, the immediate caller. And finally, use code.length to spot other contracts, but keep your eyes peeled for that constructor loophole we talked about. Mastering these single identity badges is non-negotiable for what we're building next. Which leaves us with this pretty provocative question. What happens when these individual 20-byte badges become just one tiny gear inside a massive, complex state container? Well, that is exactly what we're going to explore in our next module, putting data types together and preparing for structs. We'll literally be welding addresses, booleans, and integers into massive data structures. Until then, keep your code clean and your logic strict. This explainer was produced by Forge College. To dive deeper into this subject and explore a ton of other Web3 engineering topics, make sure to visit forge.college. I'll see you in the next schematic.